back and look at what we did with direct variation for a minute, and then we'll see how there is a nice carryover into inverse variation. Now, for example, whenever we said y varies directly as x, right? Or else when we said y is directly proportional, right? Proportional to x, right? How then did we interpret these two sentences by means of a formula? And what then did we say about that, Steve?
Y equals mn.
Y is equal to m times x, right? Where we call the number m what? This was called a, David?
Variable.
Well, the number m was, Ron?
Constant of variation.
That's our constant of variation, or else another name that we gave it was what? The constant of proportionality. Is that right? Now, let's look at another statement which we can make, in which let's say that we have y varies inversely, all right? Y varies inversely as x. Or suppose we were to say y is inversely proportional, all right? Proportional to x. And let's see how we may say that. And does anyone have any idea of how we may write a sentence which will describe this situation? Well, let me write a statement here, a sentence in which we have y is equal to m divided by x. All right, in which in this case we have, and we say that y varies inversely as x. And again, just as we had in the first case, the number m was called the constant of proportionality. So it is here, in which we have this number m as a constant. All right, and notice the pattern here of m over x. Let's look at a graph. What I'd like to do is to come back and look at, again, a direct variation in which we have y is equal to 3 times x, in which we know that the point at the origin must satisfy this sentence. Is that right? And what then is our slope number? And our slope number is 3. So if we come out here 1, and let's rise what? 1, 2, 3. And through this point our graph must go. And of course, from what we have studied thus far, what is the name for this function, if we had to give this a name? In terms of, this is a special case of what function? Well, what is its graph going to be? Its graph is a, Brenda? Is a line. And so what name did we give this function? It was a what? It was a linear function. Is that right? In which its graph is going to go through these 2 points, and in fact it's going to be in this pattern. Is that right? Now, this is a special case of what we may think of as y is equal to m times x, where m is what? M happens to be positive. Is that right? And in fact, this is a special case of a linear function. All right? Now, let's look at a second graph in which let's consider now y is equal to a negative 3x. And what's our slope number in this case? What is the slope number? Negative 3. I think you'll agree that the point must pass through the origin. And a slope number of negative 3, let's decide to run 1 unit to the left. And let's go up 1, 2, 3 units. And through this point we also have our line, which must pass through that point. So through these 2 points we have a line in which it looks something like this. Here's a special case of what we may think of again as y is equal to m times x. In this case, what can we say about m? M is less than 0. All right? Is this a function, by the way? Do we have a function here? Is this an example of a function?
Yes.
And I think you will agree that it is for any one value of x. Is that right? For any one value of x, there exists one and only one value for y. All right? What then do you think is the domain of this function? What values can we take on here for x? What set of numbers can we have here for the number x? And what can we say there, Brenda? All the real numbers. X belongs to the set of real numbers. What can we say about the range? Let me use this notation. The range of y is such that y and y, of course, are all values along our ordinate values here. And what numbers can y take on? And Brenda says, again, the set of all real numbers. Okay? Now this is, of course, these 2 examples, 1 and 2 here, refer to a linear function in which it is a direct variation function. Is that right? Now, what I'd like to do is to look at this case of 4 over x. Y is equal to 4 over x, which is a special case of this inverse variation. All right? Now let's see what the graph is going to look like. For example, let's take some numbers for x and find out what values for y we have and see what the graph is going to look like. Well, let's take x to be, say, now of course there's one number that x cannot be just by looking at a sentence. X cannot be, what, 0. Okay. So let's take a value of x, say, is 1, and we have what? 4 over 1 is 4. So 1 comma 1, 2, 3, 4. This point must be on our graph. Suppose x, say, is 2, and we have what? 4 over 2 is 2 comma 2. This point must be on our graph. Now I think we'd better take a few more points here. Suppose x, say, is 4. 4 over 4 is 1, 2, 3, 4 comma 1. This point is on the graph. Let's take a value, say, of 8. All right? Suppose x is equal to 8. 4 over 8, of course, is 1/2. So there's 4, 5, 6, 7, 8. And that has a point here associated with it of 1/2. And so this point must be on the graph. Let's take x to be say 1/2. Suppose x is 1/2. 4 divided by 1/2 is 8. So when x is 1/2, we're up here at 4, 5, 6, 7, 8. This point must be on our graph. So it looks like our graph is going to, if we were to make a nice smooth curve through it, it looks like it's going to look something like this. Let's take some values of x which are negative and see what happens. Suppose x, say, is -1. 4 divided by -1 is -4. So -1 comma 1, 2, 3, 4 has this point on our graph. Suppose x, say, is -2. -2 comma -2. So if we come out here -2, we'll come down -2. This point must be on our graph. Suppose x, say, is -4. 4 over -4 is -1. So here's a -4 comma -1. Suppose x, say, is -8. 4 divided by -8 is -1/2. Is that right? So there's -4, 5, 6, 7, 8, comma -1/2. Suppose x, say, is -1/2. 4 divided by -1/2 is -8. So here's -1/2, comma -8. There's 4, 5, 6, 7, 8, and this point must be on the graph. Now, if we can assume that we have all values of x in our domain here except 0, okay, let's see what our graph is going to look like. If I were to draw a nice smooth curve through these points, I think you would agree that it would have to come on down through here and on down through here. Let me put some arrowheads to indicate that it goes on forever. And now notice here, in our first quadrant, the graph is going to have to pass through these points, and through these points, through these points, and so on forever in this fashion. Now, this is one graph. It happens to have two parts to it, but we think of this as one graph, and it's given a special name, and we call this an hyperbola. All right? An hyperbola. And if we think of this as a function, we can call this an hyperbolic function. And we're going to study this in more detail, perhaps in an Algebra 2 course. But right now, we may think in terms of this inverse variation function in this pattern right here. By the way, this is a special case of y is equal to m over x, where what can we say about the number m? M is what kind of a number? M, in this case, is greater than 0. And notice that our graph consists of these two parts, and notice also that they are in this case in the first quadrant and in the third quadrant. Okay? Let's look at another picture. Suppose we were to consider the graph of y is equal to a -4 over x. All right, let's make its graph and see what happens. Suppose, say, x is, again, let's take x to be 1. And what do we have here? If x is 1, we have what? -4 divided by a -1 is 4. Is that right? So when x is 1, is that right? When x is -1, right, y must be 4. So when x is -1, we're up here at 1, 2, 3, 4. This point must be on the graph. If x is -2, y must be 2. So when x is -2, comma 2, this point must be on the graph. If x is -4, y must be 2, 3, 4, comma 1. If x is, say, -8, y must be what? 1/2. So here's 4, 5, 6, 7, 8, comma 1/2. Is that right? Suppose x, say, is -1/2. If x is -1/2, y must be 8. There's 4, 5, 6, 7, 8. This part must be on our graph. Our curve is going to look something like this. Now let's take values of x which are positive. Suppose x, say, is 1. -4 over 1 is -4. Here's 1 comma 1, 2, 3, 4, -4. This point must be on the graph. If x is 2, y must be negative 2. If x is 4, y must be negative 1. If x is 8, y must be negative a half. If x is a half, y must be negative 8. There's 4, 5, 6, 7, 8. Is that right? And I think now through these points we can make a graph which is going to look something like this. Passing through these points, a nice smooth curve to indicate that we have all values of x along there and all values of x along here, and also the corresponding values for y. Now, here is a case in which we may write y is equal to m over x, in which m is what kind of number? M is what? M is less than 0. And notice that our graph is in the second and the fourth quadrants when n is less than 0. Okay? Now actually, most of the time we're going to be concerned with this case here in example 3, in which m is positive. Just as most of the time in the direct variation we were concerned with m to be positive, in which it was similar to this case 1. Okay? Now, again, this curve is still called an hyperbola, and is it a function? Is this a function?
Yes.
Yes? Now, what can we say about the domain of this function? The domain with respect to x, what values of x can we take on here? And let's just look across the graph here, and what numbers do we have here for x? X is the set of what? Brenda says? All real numbers except 0. X belongs to the set of real numbers, comma, in which x is not equal to 0. Perhaps I could have written the word and. And how about then the range of y? What values do we have here for y, both for this function and in fact for this example in 3, in which we have, I think, the same range. What values can we take on for the range? Steve?
All real numbers except 0.
All real numbers except 0. Y belongs to the set of real numbers, and y is not equal to 0. Okay? Well, let's go on and look at some applications of this idea of the inverse variation function. Suppose we had a situation in which if y varies inversely as x, and y equals 6 when x equals 2, find y when x equals 3. A very simple little problem here. Again, if y varies inversely as x, as soon as we read that, give me a sentence which will interpret that English sentence. Ron says,
Y is equal to m over x.
y is equal to m over x. Okay? Now, in particular then, we have, for some value of y, which we'll call y sub 1, we have m over x sub 1. Is that right? With a corresponding value for x sub 1. And also, for some particular value of y sub 2, we have m over x sub 2. All right? Now, let's look at this and multiply both sides through by x sub 1, in which we'll have x sub 1 times y sub 1 is equal to m, and here we have x sub 2 times y sub 2 is equal to m. Therefore, what is our conclusion? What can we say here about x sub 1 y sub 1 and x sub 2 y sub 2? And what can we say? Anyone? Jane?
X sub 1 over y sub 1.
Well, we have this in the form of multiplication here. We have x sub 1 times y sub 1 is m. Well, if a is equal to m and b is equal to m, what is your conclusion about a and b? Steve, they are equal. Therefore, what can we say? X sub 1 times y sub 1 is equal to, Steve?
M.
Well, yes, they're both equal to m, but I'd like to now say that they are equal to, Bob?
X sub 2 y sub 1.
All right, x sub 2 times y sub 2. Now notice here we have 4 numbers, x sub 1, y sub 1, x sub 2, and y sub 2. And with respect to the original data, we will have 3 of those values that we know, and hence we can find the 4th. For example, we have y is 6 when x is 2. So when x is 2, let's call that the number x sub 1. All right, y must be what number? Y sub 1 here is 6 is equal to, find y when x is 3. So let's let x sub 2 be what number? 3 times, now let's consider this as y sub 2. Now, simply looking at this, therefore what is our conclusion about y sub 2? Y sub 2 is equal to, Steve? Is equal to, what can we say here? Ty?
4.
Is equal to 4, is that right? Well, we have what? 12 divided by 3 is 4. By the way, what is the number m equal to in this case? What is this constant of proportionality equal to? Brenda? 12. Is equal to 12, is that right? Here is the number m, which is 2 times 6, which is indeed this number 12, okay? Well, let's look at a second example. And in this case, we have the volume of the gas at a constant temperature varies inversely as the pressure. When the pressure is 16 pounds per square inch, the volume is 45 cubic inches. What is the volume when the pressure is 20 pounds per square inch? All right? Now, let's come back to the first sentence here, in which it says the volume of a gas at a constant temperature varies inversely as the pressure. So the volume varies inversely as the pressure. Who can give me a sentence which will translate this? Let's say V be the volume and the number of cubic inches, and let's let P be the number of pounds per square inch. Kirby?
V equals M over P.
V is equal to M over P. All right? And I think everyone will agree that this is a sentence which will translate our first English sentence in the problem. Now, just as we did in example 1 over here under C, let me now put in some subscript notation, in which we have V sub 1 is M over P sub 1, and what else can we say? Kirby?
V sub 2.
V sub 2 equals
M over P sub 2.
M over P sub 2. All right, therefore, let's now multiply both sides here by P sub 1, and we have what? P sub 1 times V sub 1 is M, and also what? P sub 2 times V sub 2 is M. Therefore, what is your conclusion, Kirby?
That P sub 1 times V sub 1
P sub 1 times V sub 1
is equal to P sub 2 times V sub 2.
P sub 2 times V sub 2, okay? Now, here again, we have 4 variables in which we know 3 of those numbers, okay? So, let's come back then to our original problem. When the pressure is 16 pounds per square inch, the volume is 45 cubic inches, all right? So when the pressure is what number? 16 times V sub 1 is what? 45 is equal to, what is the volume when the pressure is 20? So what then is P sub 2? 20 times V sub 2. Now let me rewrite this in a somewhat different pattern. Suppose we said V sub 2 then is equal to, let's write this as 16 times 45. Notice I'm not going to multiply those numbers out. Let's look at the number 20, and of course 20 factors into what? One set of factors would be what? 4 times 5, and of course 16 over 4 has a name of 4 times 45 over 5 is 9. I'm using one of our theorems, a few of our theorems that we've been dealing with, and of course 4 times 9 is 36, and we have then V sub 2 is 36. Okay? Therefore, let's now write our sentence, which is our English conclusion. What is the volume when the pressure is 20 pounds per square inch? So what can we say? The volume is what? 36. What is our unit that we're working in? 36 what? Cubic inches. Okay. Well, I think that's all that we need to do for today. So let me give you your assignment for next time, which is assignment 8.